Hello everyone. So at the end of the previous chapter on material behavior, we had arrived at a closed system of equations. Uh, and what I'm going to discuss next, as I have written down here by mentioning the boundary conditions, is going to be an extremely important discussion, but I have to write down a few sentences. Okay, and I think it will be faster if I just type it out. So the first important point that we have to note is that at the end of the previous chapter on material behavior, uh, we had arrived at a closed system of equations. Okay, we had arrived at a closed system of equations, meaning that uh, the number of unknowns uh, and the number of equations, they matched. Okay, the number of equations was equal to the number of equations. This is an extremely important point. Okay, so this is what we refer to as a closed system of equations. However, it is extremely important to note that however, these equations can be utilized to solve various specific physical situations. Okay, various specific uh, physical situations or various specific problems uh, only when proper boundary conditions are written. Only when proper boundary conditions that is very specific, okay, that is specific to that physical situation or to those physical situations uh, are mentioned. Okay, so the situation is like this, that for various physical situations, our governing equations, okay, our governing equations, they remain the same, but it is depending on what boundary conditions we have for that uh, physical situation, that we are going to end up with different solutions. Okay, this is an extremely important point to note. Okay, so our governing equations remain the same, but the boundary conditions are different, and it is based on those boundary conditions that we end up with different solutions that are specific to the problem. Now, uh, these boundary conditions, uh, they can be specified in a number of different ways. Okay, they can be specified over the entire surface of the body under consideration, in different ways. So the first way, okay, so the first way is that over the entire surface of the body we have the traction specified. So over the entire surface of the body, tractions are specified. Next, we have that over the entire surface of the body, it is the displacements that are specified. Okay, and it can also happen that we can have a mixture of the two. Okay, so maybe, so over a part of the surface, maybe tractions are specified, and over the rest of the surface, displacements are specified. So it can happen in these different ways. So diagrammatically, what is usually done is to represent this in this fashion, that suppose we have this kind of a general three-dimensional body. So it is so these arrows, they represent various tractions acting on the body. Okay, so these are the various tractions. So this is the first case. The second case is where the displacements are specified. So there we have again this three-dimensional body, but now over this entire surface some kind of displacement boundary conditions are specified. Okay, so here this dotted line means that the displacement from this original position to this thing, this dotted line, that is specified. It could happen as a very special case and a very very common case that those displacements are specified to be zero. Okay, that is also very common. I mean, that is quite the common case. And number three, we have this general body such that over a certain part of the surface, maybe from this part to this part, we have the specification of tractions like this. Okay, so over this entire part represented by this double line, I have the specification of the tractions, and over the rest of the body, so over this I have the displacements specified. Okay, so again this dashed line, it represents the displacement. So this is the third case. So that's how it is represented diagrammatically. Now let's see how we can how these things can be actually represented mathematically using all the things that we have been discussing till now. Okay, so as our first example, we'll take this kind of a situation. So we have a example of boundary conditions. Okay, example. So we have this kind, this wall, and suppose we have a beam like this, okay, or a slab like this, and here on this surface I have some traction specified, okay, where basically a uniform force F is acting. So this is my wall here, where the beam or the slab is just clamped. And you also note that that I'm choosing my coordinate axis in this fashion, that I have my x-axis like this here, flush with the bottom surface, and my y-axis here, okay, flush with the wall. And let's say that the length of this beam or slab is A, and let's say the height of this thing is B. Okay, so this will help us, these geometric parameters will help us in a very specific or in the specification of the boundary conditions. So let's take the various edges of this geometry one by one. So first of all, we are going to take the edge on the right. So that is represented by x equal to A. So at x equal to A, and we are going to do this in a very systematic fashion. So what we'll do is we'll just start out with this general Cauchy's relation. Okay, so where T is equal to sigma transpose, very generally writing this dot n, and you know that the sigma transpose is equal to sigma. Okay, now this basically will comes out as Tx is equal to sigma xx nx plus sigma xy ny, and Ty is equal to sigma xy nx plus sigma yy ny. I am not going to go into the detailed discussion of how we go from here to here. Okay, so based on our previous discussions, you should be able to write this, or you should be able to figure this out very quickly. Now, when we are talking about the edge x equal to A, you note what is this Tx. Okay, so this is the F is the it is like the force per unit area. It is not the directly the force. Okay, so this Tx, this is going to be F itself. Okay, now you note that at x equal to A, what is Nx and what is Ny? nx is basically the x component of the unit outward normal, and that is nothing but 1, and this ny is nothing but 0. So what we have from here is basically that f is equal to sigma xx, which is very intuitive. Okay, but we have arrived at this in a systematic fashion. Ty, however, is 0, and again nx is 1 and y is 0 because we are still talking about the same surface. So this gives us basically that 0 is equal to sigma xy. Okay, so that is the first set of boundary conditions applied on the edge x equal to a. Next, let us go to the top surface. That will be given by the by y equal to b. At y equal to b, what do we have? So we can do a similar sort of thing. We can start out like this. We can write the tx and ty, and now you note that on the top surface here, the tx is going to be equal to 0, and the ty is also going to be equal to 0. All right. So however, on that top surface, what we need to note is that the nx this time, that is going to be 0, and the ny, that is going to be 1. Okay, so I can write this here also. So nx is equal to 1 here, and ny is going to be 0. This is very important. So if we do a similar sort of thing, then what we'll obtain from the tx equation is that 0. So both tx and ty are 0 for y equal to b. So tx equal to 0, that is equal to sigma xx nx plus sigma xy ny. That is going to give me sigma xy as 0. Next, for the ty, I have this thing 0, and sigma xy nx, that is 0 because nx is 0, and sigma yy will be left because ny this time is 1. Okay, so we have sigma xy equal to 0 and sigma yy equal to 0. Next, for the edge y equal to 0, that is the bottom surface. Okay, so at y equal to 0, what we have again is nx equal to 0, but ny this time is equal to -1. Okay, so let's do this a little more systematically compared to y equal to b. So what we'll again have is Tx is equal to sigma xx nx plus sigma xy ny. Tx is 0, so also is ty. Nx is 0 and y is -1. Note, it doesn't really make a difference because tx happens to be 0, so we actually end up with sigma xy is equal to 0. Next, at sorry, I have to complete the ty part. Ty is equal to sigma xy nx plus sigma yy ny, and again nx is equal to 0 and y is equal to -1 because we are talking about the surface at the bottom surface where the unit outward normal is pointing opposite to the y direction. So again ty is 0 here, so overall what we'll have is sigma yy is equal to 0. And finally, for at x equal to 0, so basically we are talking about this edge, okay, the edge which is clamped to the wall. So for that it is very easy. As you can easily see, the only two conditions that we need to impose over that entire edge is that both the x component of the displacement represented by this u, that is 0, and v is equal to 0. We don't need any other condition here, so we do not specify anything here in terms of the tractions. It is important to note that where we have the the boundary conditions specified in terms of the displacements, we don't have them represented in terms of tractions, and where we have them represented in terms of tractions, we don't have them represented in terms of displacements. So let us take another example. Go to the next page. So we consider a situation like this. So this is our wall again, and we again have a structure which is clamped to the wall, but which has a triangular shape like this. Okay, so which is this kind of a triangular shape. So this is our wall here. Now the loading on this is acting in the vertically downward direction here. Okay. Now because we have these straight edges, it will be convenient if we set up our coordinate axis uh, along those directions. Okay, and what we'll do is we'll set up our y-axis like this at this corner, and we'll set up our x-axis like this, so flush with the top edge. Uh, let's name the vertices. So this vertex is A, this is B, and this is C. Okay, so now we want to write down the boundary conditions for these different edges. So first of all, let us take the edge AB. So at y equal to 0, you please note that this top edge here, that is the y equal to 0, because the y is pointed downward here. Okay, so for that, first of all, we note that nx is equal to 0 and ny here is -1. This is very, very important. Okay, please do not make a mistake here, because the y is pointed downward here. This top surface, the unit outward normal to it will be like this, pointing upward here, but that upward direction is the negative 1. Okay, so please don't make a mistake there. So again, just like before, we are going to write down the two different components of the traction. In the previous example, we had, although I did not mention it, we implicitly considered this to be a two-dimensional problem. Similarly, here we are considering this to be a two-dimensional problem. I mean, our ideas can very much, very easily be extended to three-dimensional, but for learning purposes, I think it's cleaner to talk about these two-dimensional examples first. So we have, just like before, this Tx is equal to sigma xx nx plus sigma xy ny. Now note that this Tx here, the x component of the traction on this top surface AB, that is 0. The nx is 0, the ny is -1. Okay, so we actually have 0 is equal to minus of sigma xy, but we don't need to use that minus. Next, for the y component, we have Ty is equal to sigma xy nx plus sigma yy ny. Again, this nx is 0 and y is -1. But please note that this Ty, what is this? Okay, so I have not specified it here, but you can understand that this will have, this will be like a f or some p, whatever. So this Ty, is this f or is it -f? This is very important to note. Okay, so please note that Ty is actually oriented along this y direction. Okay, now you don't confuse yourself with the unit outward normal. The Ty, the positive direction of the positive convention of the Ty is very much pointing downward, and the applied load represented by these blue arrows they are also represented by this F, okay, this force per unit area F, and so this one will be very much F, which means, and this is interesting here, that we get sigma yy is equal to minus F. This is very important to note, because you note that suppose you were to take a little element here, okay, suppose you were to take a little stress element here, and if we zoom into that stress element, even though our y is pointing downward, this sigma yy component here by the positive convention would be very much pointing upward, and because it is pointing upward, it makes sense for this final result of our, or the final representation of our boundary condition there in the y direction to be represented in terms of the minus F. Okay, so I urge all of you to be absolutely honest with yourself while you are trying to understand this. Okay, take some time to really go through this in detail, think about it very hard, okay, and convince yourself that this result that we have obtained, the sigma yy is equal to minus F, is indeed the correct representation of the boundary condition there. Next, let us go to the edge BC. Okay, so this is the interesting thing here, the BC, which is tilted. Now, although it is tilted, the good thing about it is the slope of this line is a constant because it's a straight line. Okay, this is not a curved kind of line here. So because it's a straight line, no matter which point we look at, the unit outward normal is not going to be as easy as this edge or this edge and this top edge. So both the nx and the ny components will be non-zero. They will have some value, but they will have a constant value all along this BC. So that's the important thing to note here. So let's write down the boundary conditions for the edge BC. So along BC, okay. So along BC again we'll have. So this time we cannot write that nx is equal to 0, ny equal to 0. So both nx and ny they will be non-zero. That much I can write. Okay, so they will be some cos theta and sin theta. Okay, based on what angle is specified here. So or here, doesn't matter. You can figure that out. The important thing to note here is that this general equation, which we have been using time and again in the previous example as well as in this example, the Tx as sigma xx nx plus sigma xy ny, that remains undisturbed. Furthermore, you note that this Tx is actually 0 here. Okay, it is 0 because you note that suppose you think of a traction of a traction vector here in this fashion. At this point, suppose you think of it like this, then this traction vector will have one y component and one x component. Okay, so it will have a y component like this and it will have a x component like this. It may be not so long, maybe like this. Okay, now it is very important to note that because this particular traction vector is 0, because we do not have any loading on this, that is why both the ty component, which is represented by this dotted vertically pointing downward arrow, and this leftward pointing dotted arrow, both of them, that is the tx and this is the ty, they are 0. Okay, so that's how this is 0. None of this is 0, so they remain. Similarly, the ty is going to be turned out is going to be 0. Let's write this down. Okay, we can't say anything more about the right hand side. So one thing good about here is that we do know the nx value, we do know the ny value, we do know the nx value, we do know the ny value. There will be some finite values depending on what angles are specified here. Okay, the angle ACB or the angle ABC, something will be specified there, or the length will be specified, so we know the values. Okay, next along the line AC. Okay, along AC, or I can write this as AC, or equivalently I can write this as uh, x equal to A. So if you can imagine that uh, this length is A. Okay, so at x equal to A, what we'll have, just like before, is u equal to 0 and v equal to 0. So both the x and the y components of the displacement, they are 0. Okay, now it will be very, very interesting for you to think what could perhaps happen if we have some kind of a curved line here. So instead of this kind of a nice triangular shape, suppose we have another example here like this. Suppose our wall is like this, and the top edge is like this, but suppose our bottom edge is like this. Then what? Well, you have to realize then, and suppose our loading remains unchanged. Okay, so our loading is like this, vertically downward, just like before. But now, because of this kind of an edge, we have to understand that at every point the values of nx and ny are going to change. So as we move along this curved line, the values of nx and ny, they are going to change, unlike this BC here, where this nx and ny, they were constant. Okay, so nx and ny values are constant here. Okay, so along this, uh, the nx and ny values will be known if you know the equation of this curved line, but these values are not constant. This is very important. All right. Uh, Now, as a final example of something a little bit more advanced, what happens if we do not have this kind of, so if we just quickly take a look, if we don't have this kind of a free surface, or this kind of a surface on which directly some loading is acting, rather uh, we have, suppose, uh, an interface like this, where on one side you have one material and on another side you have another material. What happens on this kind of a boundary? Okay, so this is an example. So suppose you consider, and this is a very, very common consideration, that you have what is referred to as a perfectly bonded interface. So when you have a perfectly bonded interface, so it is like these two. So you understand that here you have a bulk of a material 2, here you have the bulk of the material 1, and they are maybe glued or pasted together by a very good adhesive. Okay, so that bonding is referred to as a perfectly bonded. Okay, so there is no relative motion between the two. Okay, so what are the boundary conditions that need to be specified there? Well, this is a very general kind of thing, and you have to understand that in such a general problem, your x and y axis will be in some general fashion like this. Okay, so what is done here is to set up at any generic point here a local unit outward normal like this, and another axis which is tangent to this curve at that point. Okay, so this line is tangent to that. Okay, so this is referred to as the s axis. Okay, so s is along the surface and n is along the normal. So this is like the local coordinate axis, which helps us to specify the boundary conditions, and the exact specification of the boundary conditions is done in this fashion. So uh, what is done is, so physically what is done is to ensure that both the displacements, okay, both the displacements and the tractions are continuous. So we write that down, that for a perfectly bonded interface, so both the displacements and the tractions are considered to be continuous. Okay, so we could, I mean, write a general theory for this or write the general representation of this, but I think it makes more sense to take a little example like this. So suppose you have a uh, an annular composite cylinder kind of situation where so this is the inner cylinder, annular cylinder, and this is another material or another outer cylinder here. Okay, so let's say this is made of the material 2 and this is made of the material 1. Then what happens on this interface? Okay, the interface like between the two. So what you have to ensure is that, and suppose you consider that this is very axisymmetric situation. Okay, so there is no variation along theta direction, there's a perfect circle and so on and so forth. So basically what is done is that the radial displacement is considered to be equal here, if you're looking from this side or if you're looking at that side. So what is done is that the value of the displacement, okay, let's say the radial displacement is represented by this UR. The radial displacement at this, okay, so let's say at the interface, that is equal to the radial displacement for the material 2 at the interface. Okay, but this is not enough. You also have to write down the equivalent uh, traction conditions. So from those traction conditions, what we will obtain is that sigma RR is at the interface. Okay, from this side, from the side of looking from the side of the material 1, that is equal to sigma RR2 looking from the side of the interface. Okay, and you can also think about, okay, so think about what will happen. Think about the other components, the other shear components. So sigma, the other component will be sigma r theta here, and sigma rz. Okay, so in a very general situation, I want you to think about this thing. Okay, and we will in all likelihood take up examples of this once we go into the 2D elasticity chapter. Okay, so with this we'll close this discussion of the boundary conditions, and we'll next go on uh, to a discussion of the 2D elasticity. Okay, and that's where our applied elasticity part will really the applied part of applied elasticity will really come into the picture. So with that, let me close this discussion. Thank you very much.